Yes, today we are going to discuss zeroth law and first law of thermodynamics. Before that, just we'll go through that last class. Yeah, I'm sharing the screen. There we have to see that what is the zeroth law of thermodynamics and what is the first law of thermodynamics. Before that, we have to go for this PPT. Yeah, first we have to discuss the kinetic theory of gases. What is the kinetic theory of gases? Some assumptions we are discussed in last class. Assumptions of kinetic theory of gases also we discussed in this last class. And here we have to take up what is the Maxwell's law of distribution and viscosity of glasses. In that first unit only we have that what is the main path here. The main path means molecules of a gas move continuously. So here molecules of a gas move continuously with a large velocities according to kinetic theory of gases. They collide with each other. So here what we have here, these two are collides with each other. At each collision, the speed of this direction of the molecule changes. The molecules moves in a straight line between the two successive collisions. That distance, wherever the distance is there, whatever the distance is there, that distance is called the free path. We have this formula is A, B, C. Let us consider that we are taking 4 free paths. The average distance lambda traveled between two collision is lambda is equal to A plus B plus C and D and so on by N. Where we have using here A, B, C, D. These are the free paths we are using. We are taking the words are. Then when N is the number of collision suffered by the molecules and lambda is called the mean free path. So here we can define the mean free path is as the average distance traveled by a molecules between two successive collisions called the free mean path. Okay. So here, are you able to see this uh, screen sharing? Yeah. Here, before that, mainly we have the introduction of this first law and the second law and third law. What are the laws of we have? Mainly this thermodynamics is called the branch of the physics which deals with the study of transformation of heat into other forms of energy and vice versa it is called thermodynamics. The thermodynamics is a microscopic science. It deals with the bulk system and it does not go into the molecular constitutions of matters. Okay. Here, we are taking, already we discussed about the system. Again, I am showing here, all of you observe this system. Here we are taking the isolated boundary. This is the system and this is the surroundings of that system, the surroundings and work and heat. What you are observing here, the work is transferred from system to surrounding, surrounding to system, and heat also transferring from surroundings to system to surroundings. Mainly, what is a system means? A thermodynamic system is a specific portion of matter with a defined boundary on which our attention is focused in the system. Isolated system, for example, we are taking. So here we have already discussed here. The systems are again, I am repeating this. First, before we have to know the number of systems, how many systems we have, and what are the system, what is the isolated system, what is the closed system, what is the open system. Definitely we have to know about the system. Mainly we have three systems. One is the isolated system, another one is the closed system, last one is the open system. I am not using this open system. So here isolated, closed and open system. What is the isolated system? Example is a egg or a room. An isolated system cannot exchange energy and mass with its surroundings. Okay. Come to the point of closed system. An isolated system cannot exchange energy of mass with surroundings. Okay, this is a closed system and open system. In an open system, the mass and energy both may be transferred between the system and surroundings. And you know that what is the surrounding? What is the surrounding here? Surrounding is everything outside the system that has a direct influence on the behavior of the system is known as the surroundings. Okay. So here, how the thermodynamic process is going. The thermodynamic process is a system undergoes a thermodynamic process when there is some energetic change within the system that is associated with the changes in pressure, volume and internal energy. So here, the thermodynamic system here, yeah. So here we have four types of thermodynamic procedures, thermodynamic system. So one is adiabatic process, isochoric process, isobaric process, isothermal process. We know about this isothermal process. So here, what is the adiabatic process? A process where no heat transfer into or out of the system occurs. What is here isochoric system process? A process where no change in volume occurs and the system does no work. Okay. What is the isobaric process? A process in which no change in pressure occurs. Here, all of you observe here, and in adiabatic process, heat transfer in one hour into or out of the system, and here isochoric system here where no change in volume occur, the system does no work. Okay, here come to this process isobaric system which no change in pressure. Okay, here isothermal means a process in which no change in temperature occurs. Okay, then so, thermodynamics equilibrium. What is the equilibrium? Here, what is the equilibrium, Amma? What is the equilibrium? Yes, I am telling that. Thermodynamic equilibrium is at a given state, all properties of a system have fixed values. Okay. Thus, if the value of even one property change, the system state change to the different one. In a system that is in equilibrium, suppose for example, no changes in the value of properties occur when it is isolated from its surroundings. That is called the equilibrium. And also we have mainly three types of equilibriums we have here. So thermal equilibrium and thermal equilibrium, mechanical equilibrium, chemical equilibrium. Anyone, can you read this thermal equilibrium? Anybody? Anybody who are in the line? Could you tell me the, are you able to observe the screen, ma? Rama and Shravani, I don't know who is this. Rama and Shravani? Rama and Shravani?
Yes, ma'am.
Are you able to see the screen? Amma, screen కనిపిస్తుందా మీకు? Screen కనపడుతుందా తల్లి? Okay, I will tell that. So, what is the thermal equilibrium? When the temperature is the same throughout the entire system, we consider that system to be in thermal equilibrium. What is the thermal equilibrium? When the temperature is the same throughout the entire system, we consider the system to be in thermal equilibrium. And what is the mechanical equilibrium means? The system when there is no changes in pressure at any point of the system, we consider the system to be in mechanical equilibrium. Okay. What is the mechanical equilibrium? When there is no change in pressure at any point of the system. What is the thermal? Throughout the entire system, we consider that is the thermal. Here, pressure at any point of the system, we consider that is a mechanical equilibrium. And come to the point of what is a chemical equilibrium. Here, when the chemical composition of a system does not vary with time, we consider that is to be in chemical equilibrium. Okay, yeah. Here, a thermodynamic system is said that in thermodynamics equilibrium, if it is in a chemical equilibrium, mechanical equilibrium and thermal equilibrium, and the relevant parameter cease to vary with time. So we have mainly 4 laws of thermodynamics we have. One is the 0th law of thermodynamics and first law of thermodynamics, second law of thermodynamics, third law of thermodynamics. These 4 important we have in our syllabus. And first we will see the go through this 0th law of thermodynamics. So this 0th law of thermodynamics is developed in the year 1930. Who developed this? Fowler. Fowler is developed this law in 1930. Okay. So here the 0th law of thermodynamics states that if two systems are each in thermal equilibrium with a third system. What is the 0th law of thermodynamics? If two systems are each in thermal equilibrium with a third system, then those two systems are also in thermal equilibrium with each other. For example, all of you observe this one, 0. What is the, we have adiabatic, this is adiabatic one. We have system A and system B and system C. Here, what I said before this, what is this? Two systems, if two systems are each in thermal equilibrium with the third system. Here all of you observe this system A and system B and system C. What will happen here, Amma? What will happen here in these three systems? Both the systems A and B in thermal equilibrium with the third law of thermodynamics. Third system C is separate. Okay. And here we understand that this is states that zeroth law of thermodynamics. Same thing here. A, B, C. What you are observing here, Amma? Anybody? Are you able to see the screen or? Not communicate with me. I don't know that you are listening or not. I understand that. Okay. ఇది కనిపిస్తుందా మీకు? కనిపిస్తుందమ్మా? యా. సో ఇక్కడ ఈ ఫిగర్ ఉంది కదా ABC. దీన్ని బట్టి మీరు ఏం అర్థం చేసుకుంటారు? వాట్ యు ఆర్ అండర్స్టాండింగ్ టు సీ దిస్ ఫిగర్?
When A, B is when A and the system B is in thermal equilibrium.
Very good.
And
you
when
read this one. Yeah, very good.
When A and the system C is in a thermal equilibrium,
very
then
good.
we are saying that system B and system C is in also thermal equilibrium.
Yes,
when
we are observing that B and C is the these two are the thermal equilibrium and AC also thermal equilibrium. We will see here temperature of system A is equal to temperature of system C. Okay. Similarly, system B is in thermal equilibrium with system C. Then temperature of system B is equal to temperature of system C. Okay. Here in next slide, what we can see, this is a good example for understand the zeroth law of thermodynamics. See here, we have two cups we have here, A and B. And consider these two are with boiling water. When a thermometer is placed in cup A, for example, it gets warmed up by the water until it reaches 100 degrees centigrade. When it reaches 100 degrees centigrade C, we say that is in thermometer is in equilibrium with cup A. When we move this thermometer to cup B, so to read exactly whatever happens in cup A, it will also come down, and the thermometer is also in equilibrium with cup B. By keeping this in your mind, the zeroth law of thermodynamics, we can conclude that cup A and cup B are in equilibrium with each other. Okay, yeah. What is the significance of zeroth law thermodynamics? So it provides a base for thermal equilibrium. It provides temperature as the indicator for thermal equilibrium. Thermometer functions on the basis of this law only. Okay, whatever we are using that thermometers functions on this base of this zeroth law only. Okay. Here, the first law of thermodynamics. What is the first law of thermodynamics? We need to understand the relationship between the heat and work and the concept of internal energy. What is the first law of thermodynamics? First law of thermodynamics, adoption of the law of the conservation energy. The first law of thermodynamics states that energy cannot be created or destroyed. However, it can be transferred from one form to another form. And also according to the first law of thermodynamics, heat is a form of energy. Okay, heat is a form of energy, and a thermodynamic process obey the law of the conservation of energy. So here we can state that this first law of thermodynamics, suppose an amount of heat we are taking dq or q is supplied to the system. This is used in the following three parts. So in first part, we have to take a part is used in the rising the temperature of the system, which is equivalent of increasing internal energy. That is, we are taking duk. Come to the second point. A part is used in doing internal work against molecular attention, which is equivalent of increasing the potential energy of the system. We are taking. So internal increasing point of internal energy duk suffix k, and increasing the potential energy, internal energy and potential energy we are taking here. Potential energy of the system dup, and finally we will tell that the first law of thermodynamics, dq is equal to duk plus dup plus dw. So dq is equal to du plus dw. How it will come? Where du is equal to, we are taking where du is equal to du suffix k plus du suffix p is increasing in internal energy of the system. That's why we are taking du is equal to du suffix k plus du suffix p. Okay. And come to the one example I am giving here. First law of thermodynamics. A thermodynamic system is equilibrium state process, a state variable known as the internal energy. Between these two systems, all of you observe these two systems. What will happen here? Between these two systems, the change in the internal energy is equal to the difference of the heat transfer into the system and the work by the system. So here all of you, what is the key Q? What is the Q? Q is the heat transfer. What is the W? Here, work. Okay.
Work.
Yeah, work. So all of you understanding about this figure, no? Yeah, what is the first law of thermodynamics? Okay. Yes. What is the significance of thermodynamics? What is the significance of thermodynamics? We will read here. It represents the energy that can be transferred from one body to another body. Suppose we are getting fever. How you identify this much of fever you have? Anybody? Please. Suppose you are getting fever. How you recognize that I have 100 degrees centigrade fever? How you can understand that? The temperature transfers from one body to another one. The temperature transfer from ours to thermometer. Okay, but it cannot be created nor destroyed. Okay, dq and dw changes throughout the process. However, throughout the entire process, finally du is equal to dq minus dw is the first law of thermodynamics formula. Here u is what u is change in internal energy we are taking. Q is a heat added and W is the work done by the system. This is, we will tell that first law of thermodynamics and significance of thermodynamics. What are the limitations of first law of thermodynamics? The first law of thermodynamics will not show the direction of changes. This law fails to explain the heat flow. Okay, if the rod is heated, the heat flows from one hot end to the cold end, and these are the limitations for this law. The amount of energy transfer is only described in the first law of thermodynamics. Okay, what are the applications of thermodynamics? We don't know, we are learning, but we don't know the applications of that one. For example, here you are learning the in the laboratories, you are learning the thermistor experiment. So in that, what we observe that thermistor is used for measure the temperature. Okay, we are using in that experiment in in characteristics of thermistors, we are using that thermistor is used for to measure temperature. We have so many examples and uses of that thermistor. We can use that thermistors in where we calculate this temperature. Anybody? Yes, here that thermistors used for use in our heaters and wherever the greasers and wherever the temperature we calculate and wherever the temperature we are using, wherever the calculating temperature we are using here, there we are using that thermistors. Here also the applications of first law of thermodynamics is we are using this first law of thermodynamics, refrigerators, thermal power plants, engines, and here also some applications we have isothermal process. In isothermal process, we use this first law of thermodynamics, and adiabatic process, we use this isochoric process, isobaric process, a cyclic process. We are using this. These are the applications for first law of thermodynamics. And here we have the applications of first law of thermodynamics, reversible and irreversible process. We have that is also in our textbooks, reversible and irreversible process. Here. Yeah. In your textbooks, we have that reversible and irreversible. In third unit, we have that. There what we have here, reversible and irreversible. Volume, temperature and pressure we are using in this our textbooks. The characteristics of reversible and irreversible process can be understood well by considered by the typical thermodynamic system. Here we are using the volume, temperature and pressure. I will tell here easily. Application of thermodynamic also we have here another application. Isothermal process. In isothermal process also we use for this is the application for first law of thermodynamics. And isothermal process is a change of thermodynamic system in which the temperature remains constant, that is dT is equal to 0. Hence, there is no change in the internal energy of the system, that is du is equal to 0. We will calculate this isothermal system with this equation. dq is equal to du plus dw, dq is equal to dw. So, this formula adiabatic process we are taking, dq is equal to du plus dw. Now becomes the first law of thermodynamic applications we have. And here also du is equal to minus dw for this adiabatic process. We use this equation. And isochoric process also we use this first law of thermodynamics. dq is equal to du plus dw. Now becomes, as we can write that dq is equal to du. And here a cyclic process also we use here. And cyclic process, you see that the system returns to its initial state. The changes in internal energy must be 0. That is the condition of this cyclic process. The first law of thermodynamics, this a cyclic process, we use the dq is equal to du plus dw. Now become, as we will write that dq is equal to dw. So here also isobaric process also we have in first law of thermodynamic application. So this process one which a gas does work a constant pressure. The amount of heat is partially used in one part or two parts we will use in increasing the temperature and partly use in doing external work, that we will calculate this isobaric process is dq is equal to cp dt plus pdv. So here what is the reversible and irreversible process? We will discuss this here. We see so many changes happening around us every day, such as boiling water, rusting of iron, melting ice, burning of paper, etc. These are we observed in our real life every day. In all these processes, we observe that the system in consideration goes from an initial stage to a final stage, where some amount of heat is absorbed from the surroundings and some amount of work W is done by the system on these surroundings. This process we observe this every day, and here now for how many such systems can the system and the surroundings be brought back to their initial state? Anybody? With a common example, I am telling here, such as rusting and fermentation, we can say that it is not possible in most cases. Okay, and here reversible process is a thermodynamic process is said to be reversible if the process can be turned back to such that both the systems and the surroundings returns to their original state, which no other change anywhere. Okay, here in our textbooks, if you have with the textbook, number 41 page, unit 3, we tell that for example, we are using in that cylinder M we are taking, whose walls are ideal heat. Insulators with the base being a good conductor be placed in a large heat reservoir maintained at a temperature T. As illustrate that, we have one figure in that we are using equilibrium state, and let us now try to change the system to another equilibrium, one equilibrium to a state in which the temperature T is the same as that of initial state, but the volume is reduced to half its original value. So here in our textbook, that is the reversible process. And here this process is idealized and does not occur naturally, but it serves as a theoretical framework for evaluating the maximum efficiency of real process. So some conditions we have the process of reversible process. So conditions for reversibility, there must be total non-attendance to disparate forces such as friction, viscosity, electric resistance, etc. These are the example for this conditions we have. In this, we cannot do this reversible process. Okay, the direct and inverse form must take place very slowly. The temperature of the system must not vary from its environment. Okay, examples for this reversible, you understand that all isothermal and adiabatic changes are reversible only. On the off chance that they perform in the exceptional, slowly it will increase. Okay, here in reversible process, when a certain sum of heat is retained by the ice, for example, here we are taking, it melts. In the case some of heat evacuates from its. So what we observe in ice in this reversible, what you are understanding these both examples in reversible process, these are the example for reversible process. Yeah, here what happened, the water formed within the direct process will change over to ice. Okay. And irreversible process can be defined as a process in which the system and the surroundings do not return to their original condition once the process is initiated. This is called the reversible process. So the factors due to which the reversibility of a process occurs. So we have three processes here. So factors which due to the irreversibility of a process occurs. The friction that converts the energy of the fuel to heat energy. So here the unrestrained expansion of a fluid prevents from regaining the original form of the fuel. Heat transfers through a finite temperature, the reverse of which is not possible as the forward process in these cases. So it happens in spontaneous. So mixing the mixing of two different substances, suppose for example we are taking, that cannot be separated as in intermixing process is again spontaneously in nature. The reverse of which is not feasible. Okay. Example for reversible process: cooking gas leaking from a gas cylinder in the kitchen, for example, diffuse to the entire room. The diffusion process will not spontaneously reverse and bring the gas back to the cylinder. Okay. And another example we have in reversible process, the stirring of a liquid which is in thermal contact with the reservoir will convert work into heat, increasing the internal energy of reservoir. This process cannot be reversed as it would lead to the complete conversion of heat into work, violating the second law of thermodynamics. Okay, here Joule's and Thomson effect is the irreversible process because on reversing the flow of gas, a similar cooling or heating effect is not observed in that experiment. Few other examples includes spontaneous chemical reactions, friction, diffusion of gases. These are the examples for irreversible process. So here, comparison between these reversible and irreversible process. In reversible, what happens? In irreversible, what happens? Here, reversible process, the process occurs infinite. Similarly, slowly it will increase. Irreversible process, this process is very speed or rapid. Okay. And in reversible process, the equilibrium is not disturbed. Here, the opposite of this reversible process, equilibrium may alter and may attain only after process completion. Here, work done is maximum. Here, work done is not in maximum. So, can be easily reversed, cannot be reversed. Can be made to proceed in the forward and backward directions. And here can occur in one direction only. Okay. So this is what first law of thermodynamics and zeroth law of thermodynamics, and come to the point of second law of thermodynamics. Here, what is the second law of thermodynamics here? The second law of thermodynamics is a fundamental principle in thermodynamics that describes the direction of natural process and the concept of entropy. Entropy is coming in second law of thermodynamics. It has several, it has several formulations, but they all revolve around the ideas that certain spontaneous processes are irreversible and lead to an increase in the overall disorder or the system and closed system. This concept is often summarized as the increase of entropy. So here several statements we have about the second law of thermodynamics. Here, before that, what is entropy? Entropy అంటే ఏంటమ్మా? What is entropy? So here the entropy is the degree of disorder or uncertain in the system. And here what is the entropy is the degree of disorder or uncertain in the system. We have several statements, so we will see that. In this second law of thermodynamics, we will see that Clausius statement, Kelvin-Planck statement, and entropy statement here. And what is the Clausius statement in second law of thermodynamics? What is the statement of the second law of, stated that Kelvin and Clausius does not separately direction of change in a chemical or physical process. Okay. Here what he gave the Clausius statement is heat cannot spontaneously flow from a colder body to a hotter body. He is given the statement. Heat cannot spontaneously flow. So, and from a colder body to another hotter body. So, for example, this experiment here, we will take that. And what about the Kelvin-Planck statements? It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce the net amount of work. He is giving that statement. So, what is the entropy statement mean? The entropy of an isolated system never decreases. It either remains constant in a reversible process or increases in an irreversible process. Mathematically, we will tell that the Carnot theorem, dq is equal to TdS if where P represent here T, what is the T, Q, V, and here also we will see equation 3. Substituting here, equation 2, 2 and 3. Here we have equation 1. So in equation 3 and for 2 and 3 in 1, what about here? We are seeing that one minute. So mathematically, we will prove that dq is equal to TdS. In down 3 and 4 equations, substituting equations 2 and 3 in one first equation. Du is equal to, we will discuss in next class this total equation of mathematically reversible and irreversible. What is the Carnot theorem? All these we will discuss next class. What is the Carnot theorem? How the formation of second law of thermodynamics, and here temperature scale. What is the temperature scale? All this we will discuss next class. Here little bit you see that you understand that for understanding purpose only I am giving this equation of Clausius differential equation relations. So this equation applies the closed system, perform PV work is only here. And what are the applications of second law of thermodynamics? The second law of thermodynamics is the heat engine model. Here what will happen? Heat engines involve a cycle of increasing and decreasing temperatures that moves a piston. The second law of thermodynamics uh, dictates that amount of work that the changes temperatures in the heat engine can produce. So, in our real life example, we are taking here, someone may place an ice cube in a glass of water. You know about this lemon juice. About lemon juice, you know that that is also one example for this second law of thermodynamics. So here, what we are taking ice cube in a glass of warm lemon, and then neglect the consume it. After 1 hour, we will see that glass. What will happen? When we will see the ice cube, what will happen? So after 1 hour, when you see that the snow has gone, but the lemon on day has chilled. What is here? Lemon on day means we have mixture of lemon juice and sugar and water. Nothing but cold juice. That is, it will chilled means lemonade mixture of lemon juice and sugar and water. Okay, this is a real example for this one. Okay, we will discuss later about the thermodynamic potential. Okay, now, right? So for next class, we will discuss about the thermodynamic potentials and thermodynamics temperature scale also we will discuss there, and Carnot cycle, Carnot engine, entropy, all these terms, entropy disorder, second law of thermodynamics terms of entropy, and also we will discuss this, we have thermodynamic potentials here, just a little bit I introduced this one. We will get internal energy, enthalpy, and permeate free energy and Gibbs free. That equations also we will discuss. What is the internal energy equation and how we will use this S and V. What is the enthalpy and what is the formulation of F is equal to Helmholtz function, Gibbs function. We will properties of the potentials. We'll discuss the next class. Okay, na? And also Maxwell relations, about the Maxwell relations also we'll discuss in the next class. Okay, thank you, Amma. Right.